Sup nerds. Today I want to talk about second order linear homogeneous ordinary differential equations with constant coefficients. Now I know that's a mouthful, but it's easier to write what these look like. They just look like AY double prime plus BY prime plus CY, where A, B, and C could be any constants. So it's second order because of the Y double prime. It's linear because the coefficients in front of each of the derivatives is just a linear function, and they're constant coefficients actually, and it's homogeneous because it's equal to 0. So these are a very special type of ordinary differential equations where if we have two solutions to the ODE and we add them, we get another solution. And if we take a solution and multiply it by a constant, we also get another solution. So let's take a look at what solutions look like. Now, a good guess from previous ODEs would be y equals e to the rt. Now, if we just computed the derivatives and plug this in, we would get some equation ar squared times our function plus br times our function plus c times our function equals 0. And now factoring out in e to the rt, we get a polynomial times e to the rt equals 0. Now, since e to the rt is never 0, that means that the polynomial must be 0. So we could use a quadratic formula to solve for r, and we know that a second order polynomial is going to have roots that change depending on the discriminant, b squared minus 4ac. So there's going to be three different cases. The first case is when this discriminant is positive, b squared minus 4ac is positive. Second case is if it's 0, and third case is if it's negative. And we'll do a couple of examples of each of these cases so you can get a good feel for it, because their solutions look pretty different depending on which case we're in. So in this first case, y double prime minus 5y prime plus 6y equals 0. The characteristic polynomial is just r squared minus 5r plus 6 equals 0, which we could easily factor and get our two roots, 3 and 2. So when the discriminant is positive, we're going to get two real roots that are distinct. And so we're going to get two solutions. We get y1 equals c1 e to the 3t and y2 equals c2 e to the 2t. And as I mentioned a second ago about linear homogeneous ODEs, sums of them are also solutions. So our general solution looks like y equals c1 e to the 3t plus c2 e to the 2t. Now, you can and should check that this is actually a solution. So if you compute the derivatives and then plug it back into the ordinary differential equation, you'll see after a little bit of cancellations and careful work that you indeed get that this solves the ODE, and we get 0. So here we'll see in different colors. The blue is the terms that are e to the 3t, and they all cancel out because it's 9 minus 15 plus 6. And then the terms highlighted in orange are the e to the 2t terms, and they also cancel out because it's 4 minus 10 plus 6. Now, you might be given initial conditions, in which case you have to solve for a specific solution. So let's just say y of 0 equals 1 and y prime of 0 equals 0. Then we want to plug this into the function and its derivative. So plugging it into the function, we get 1 equals c1 plus c2. And then plugging into the derivative, we get 0 equals 3c1 plus 2c2. And after you do this, you're going to get two equations with two unknowns. So it's a very simple system of equations, and you could easily solve for c1 and c2. As always, you should pause and think about why these are solutions and why these initial conditions are the way they are, and make sure you really understand how to solve these ODEs before moving on to the next examples. Let's do another example that's pretty similar. So in the second one, we're going to have y double prime plus y prime minus 20y equals 0. It should be a 20y. And going straight to the characteristic polynomial, we get the two roots are both real, so r equals 4 and r equals negative 5 are the two roots. And so our general solution is going to look like y equals c1 e to the 4t plus c2 e to the negative 5t. And if we have initial conditions, say y of 0 equals 1 and y prime of 0 equals 2, and plug them into the function y and the derivative, we could easily solve for c1 and c2. Two equations, two unknowns. It's a little trickier than the previous one, but still not too bad. We get c1 equals 7/9 and c2 equals 2/9. Let's do a different type of example now. Let's take our ODE to be 2y double prime plus 2y prime plus 5y equals 0. Now when we look at the characteristic polynomial, we'll get the discriminant 4 minus 8 times 5 is negative 36. Our discriminant is negative. So our roots are complex. In this case, negative 1/2 plus or minus 3/2 I. And so we can still plug these into the function and get y1 is c1 e to the negative 1/2 plus 3/2 it, and similarly for y2. But this is kind of weird because these are complex functions. So this is where we want to use Euler's formula. So Euler's formula is e to the I theta equals cosine theta plus I sine theta. It's a pretty important formula in complex variables. So using this, we could expand out what y1 and y2 in terms of cosines and sines. So we want to take the real part of the exponent and the imaginary exponent and split them up. So we get y1 equals e to c1 e to the negative 1/2 t times cosine of 3/2 t plus I sine 3/2 t. And then y2 is similar. It's c2 e to the negative 1/2 t times cosine of negative 3/2 t plus I sine of negative 3/2 t. But if you think about how cosine and sine behave, cosine is an even function. So cosine of negative something is equal to cosine of that something. So cosine of negative 3/2 t is really cosine of 3/2 t. And sine is odd. So sine of negative 3/2 t is negative sine of 3/2 t. So these are our y1 and y2. And as I mentioned earlier, the sum of any two solutions is also a solution. So if we take the sum of these two, we'll see that the sine terms cancel and we just get some constant e to the negative 1/2 t times cosine of 3/2 t. And their difference, which is some constant times e to the negative 1/2 t times sine of 3/2 t, those are also solutions to our differential equation. Now these constants c are still arbitrary. If we take them to be real values, then these are real solutions to our ordinary differential equation. And that's good because that's what we wanted. We don't really want complex solutions, we want real solutions. So definitely pause and think about how Euler's formula works. Maybe do some practice problems. I'll go into more depth about Euler's formula in a future video, but for now you could just take this on surface level. You should always check that these are indeed solutions. So let's just check the first solution. So e to the negative t over 2 times cosine of 3/2 t. If we take the derivative, we have to do product rule. And then for the second derivative, there's going to be two product rules. So I'll write them in different colors. Product rule of the first term is in blue. Product of the second term is in purple. Once you've carefully taken each of these derivatives, you can plug it back into the differential equation. Again, you have to be careful because there are constant coefficients to factor in. We're not just adding these three equations. So let's just look at the cosine terms. Okay, so there's a bunch of sine terms as well, but let's just look at the cosine terms. So the cosine terms that arise from y double prime, we need to multiply by 2. So I'll do this in green. So from y double prime, we have 2e to the negative t over 2 times 1/4 minus 9/4. So the two terms underlined in green. And then in pink, the terms from y prime, we need to multiply by 2. So there's one cosine term in the y prime equation, just the first term. So we write this as 2e to the negative t over 2 times negative 1/2. And then from 5y, we could write in brown the one cosine term. So we get 5 times e to the negative 2 and times 1. So if we factor out e to the negative t over 2, we see that it's just 4 minus 1 plus 5, which is 0. So all the cosine terms cancel out. And I highly suggest pausing and working out the sine terms as well and showing that they all cancel out. And this indeed does solve the ordinary differential equation. As always, pause the video and go back and go over any parts that you might be unclear about. And you could always watch it slower if need be. So let's do a similar example. For this fourth one, y double prime minus 8y prime plus 20y equals 0. So we get our characteristic polynomial. And for this characteristic polynomial, we get that the discriminant is negative again. It's going to be 64 minus 80, so negative 16. And so we could write the roots of this characteristic polynomial as 4 plus or minus 2i. Okay, so 4 is the real part and 2 is the imaginary part. And so just like the previous example, we're going to have y equals c1 e to the real part, 4t, times cosine of 2t plus c2 e to the 4t times sine of 2t. Again, pause and work through any additional examples, or go through this again a little bit slower if you need to. For this fifth example, let's look at y double prime minus 4y prime plus 4y equals 0. Again, that last term should be 4y. So the characteristic polynomial is r squared minus 4r plus 4, which you probably factor by inspection. It's r minus 2 times itself. So our solution will look like y equals c1 e to the 2t. So we know that that's one of the solutions. And now I claim that another solution will be if we just took this and multiply by t. So the second solution is t e to the 2t, and you can multiply by some constant c2. And if you don't believe me, you should surely check that c2 t e to the 2t satisfies the differential equation. So if we look at the function and then take its derivative with product rule and then look at its second derivative, and be really careful with adding the terms, plugging it back into the differential equation. Again, I tried to do it by color, so the second derivative comes from the purple, first derivative is in the brown, and then the green is just the function itself. You get that it does satisfy the ODE. So there's a lot of deep reasons why this is a solution, but for now you could just take it on face value. And whenever you have a repeated root in your characteristic polynomial, then you have the original solution that you would expect, just e to the root times t. And then your second solution would be the first one, just times t. So that's the general solution to a second order linear homogeneous ordinary differential equation with constant coefficients whose characteristic polynomial has a repeated root. Definitely pause and make sure you fully understand this before moving on to the next one. As always, pause and work through things a little bit slower if you need to. And if you have any questions, I suggest dropping them in the comments below. Now, for the sixth example, we have y double prime minus 6y prime plus 9y equals 0. And it's similar to the last one, because if we look at the characteristic polynomial of this one, its roots are both 3. So again, our solutions are going to be c1 e to the root times t plus c2 t e to the 3t. Now for good practice, if we're given initial conditions like y of 0 equals 0 and y prime of 1 equals 2, you want to plug these conditions in for our function. So c1 equals 0 just by plugging in 0 for t. And then looking at the derivative and plugging 1 into the derivative, we get c2 e cubed plus 3c2 e cubed equals 2. That comes from the product rule. And there are no c1 terms, so easily solve for c2. So now we've seen the 3 different cases where the discriminant is positive, negative, or equal to 0. So now to just go over the general strategy when you have a second order ODE with constant coefficients and it's homogeneous. So we have the characteristic polynomial, and there's 3 cases for the discriminant. If it's positive, we just have y equals c1 e to the first root times t plus c2 e to the second root times t. And the next case is if the discriminant is less than 0, in which case you could work through a lot of the algebra, and you'll see that the 2 solutions are as shown, where it's still e to the negative b over 2a t times, and then cosine and sine of the arguments. The arguments comes from, we want to switch around b squared minus 4ac, so that now the square root is positive. And finally, the third case is the one we just went over, where it's repeated root, and our solutions look like c1 e to the rt, where our r is negative b over 2a, because the discriminant is 0. And the second solution looks like the first, except it's multiplied by t. That's it for today. Again, pause or go back to any parts that you were unclear about, and make sure you fully understand it. And if you have any questions, drop them in the comments below, and make sure to smash that like button. Till next time.